All right, so let's take a few minutes to go through some of the popular types of questions you're going to see on your upcoming exam. And these aren't the only types of questions, but these are the ones that deal with a lot of the reactions that we've talked about, which is pretty much made up almost this entire chapter, was reactions and mechanisms. So when it comes to reactions, you'll see like three different types. Where I give you the reactants and you show the product. And you have to think about regiochemistry, stereochemistry, all that good stuff. I might give you the products and the substrate, but you need to figure out how is that accomplished? What are the reagents? So like for example, if I gave you this and then this product, you'd have to figure out what is missing here. The other type is I'll give you the reagents. So maybe instead I give you this and you have to figure out, well, what's the substrate look like? What alkene would make that? So those are kind of the three types of questions you'll see when it comes to reactions. Again, that doesn't include stuff like mechanisms, multi-step synthesis, other questions dealing with more theory and things like that. So just kind of, I'm going to go through like these three types of questions here, just as a little practice. So example number one, here is the substrate and then the reagents. And you have to come up with the product. So for this and in the future, when we're dealing with even more reactions and more functional groups, just kind of take a look at what you're given. So we're given an alkene here. And what do you do with alkenes? Well, we can either do an addition. That was pretty much all of this chapter. Or the other thing that we just learned about in the previous lecture, oxidative cleavage. We can blow it apart. How do we figure out which one we're doing? Now we look at the reagents. Okay, so our reagents, we have BH3 and THF, and then hydrogen peroxide and sodium hydroxide. Um, so what kind of reaction is that? Well, that's a hydroboration oxidation. So in your mind, you need to start thinking about that, about what that is going to do. Well, that's going to add H and OH to the alkene. Does it have any regiochemistry? Yeah, it does. It follows an anti-Markovnikov's addition. Will it have any stereochemistry? Maybe. We have to look at our product once we draw it. Okay, so we know where everything is going. We know the hydrogen is going to the less substituted carbon, or more substituted carbon, and the OH is going to the other carbon. Now, you don't have to show the hydrogen that got added because we don't have to show hydrogens, but I'll draw it in to emphasize it's right there on that carbon. And then what's the question you need to ask yourself? Okay, I want you to yell it out at your computer right now. Did I make any chiral centers? Is there any stereochemistry here? No, I didn't make any chiral centers, so I don't need to worry about stereochemistry. All right, let's look at another one. So in this problem, you're given the reactant, I'm sorry, the substrate, you're given the product. You need to fill in how am I going to accomplish this? So ask yourself, what happened? Well, I went from an alkene and I put two OH groups across that alkene. So it's some sort of dihydroxylation. If I look at what direction those two groups are going in, that gives me a specific idea of how they added. This was an anti-dihydroxylation. Okay, so that's going to narrow down my possibility of reagents. We've only talked about two ways to do a dihydroxylation. One of those ways is with osmium tetraoxide. Will this work? What is the stereochemistry for adding osmium tetraoxide? That's not going to work because it's a syn addition. The only other way we know how to add OH groups across an alkene is to first make an epoxide out of an alkene and then do an acid catalyzed ring opening. Will this work? Yes, this is an anti-addition. So I'm going to go back to my reaction. How do I make an epoxide? Well, standard way that we know right now is use a peroxy acid, like MCPBA, and then in a second step, do an acid catalyzed ring opening with water in acid, or I should say acid in water. All right, now the last example we're going to look at is you have to figure out the substrate given the reagents on the reaction arrow and what the product looks like. All right, so again, first thing you want to ask yourself is what happened? You say, well, I don't even know what we're starting with. How can I tell what happened? Well, look at your reagents. Okay, step one's kind of a big, giveaway. Like O3, that's ozone. I mean, they named the reaction after it. This is an ozonolysis. Okay, well, what does that mean? It's an oxidative cleavage of a carbon-carbon double bond. All right, that's great. So I know my starting material should be an alkene. Now, how do I go backwards? I didn't talk about this in the previous video, so I'll go through it now. How do I go backwards in an ozonolysis? If I have the product, how do I imagine what the original alkene looks like? So remember what I said, if I have an alkene and I do an ozonolysis, I'm going to break that apart. And I said, give each carbon, or no, I said, make each carbon of the double bond a carbonyl. So how do I go backwards? Right, get rid of the oxygens and connect the two carbons with a double bond. So I want to imagine getting rid of these, and then I'm going to connect these two carbons together with a double bond. Now, for the sake of for the not argument, but for keeping track of all the atoms, I'm going to number everything here. 1, 2, 3, 4, 5, 6, 7. So notice I'm connecting carbon number 2 to carbon number 7. Just count how many carbons that is. Well, that's going to make a 6-membered ring. So let's say I've now connected 2 and 7. So this must be 6, 5, 4, and 3. Well, where's number 1? Number 1's right, still here attached to number 2. And I'm just going to put a double bond between 2 and 7. And there's my answer. All right, so these kind of give you an example of the types of reaction problems that you're going to see on the upcoming exam. Now, there'll be one more video in this set of lectures, and it's going to be very important because I'm going to go through multi-step synthesis problems. Now that we have a lot more reactions under our belt, we'll have a lot more tools to interconvert between functional groups and make larger molecules out of smaller ones.